Hello, ladies and gentlemen. My name is Peter Schaumann. I am professor for steel construction at Leibniz University in Hanover, Germany. Welcome to my presentation, Development and Challenges of Offshore Support Structures for Offshore Wind Turbines. And I like to thank Ian Burgess in particular for inviting me to give this keynote lecture. And at the beginning, I like to acknowledge my co-author of this presentation, Mrs. Manuela Bohm. She's working as a research assistant in my institute. The outline of my presentation is, at first, I'll start with an introduction to the climate change challenge and some statistical data in terms of offshore wind. Then I will introduce the different types of offshore wind energy support structures. And then I go step by step through the different research topics: grouted connections, bolted, welded connections, suction buckets, and finally corrosion. And at the end of my presentation, I will briefly sum up. Maybe you ask yourself why I put this hydrogen picture here. Wait some minutes, I will come back to that in my presentation. So, where do I work? I have been working for more than 25 years now at Leibniz University in Hanover. It has been founded in 1839. We have more than 30,000 students and 3,000 scientists. Originally, it has been a technical university. Nowadays, we have faculties in engineering, natural and social sciences. And you have seen this logo on my slide. Forwind is a joint research center of 3 universities in Hanover, Oldenburg, and Bremen in the north of Germany. It is dedicated to wind energy research in different areas in engineering and physics. It has been founded, I founded it in 2003 with 3 other colleagues. And today we have more than 300 scientists working in this area. So that's quite a big joint action between the universities in the north of Germany. So, what is our motivation? Very clearly, what we are experiencing is wildfires, droughts, hurricanes, heavy rain, and flood disasters. And it's very clear that to solve this challenge, we have to decrease carbon dioxide emission and we have to increase renewable energies. Very recently in Germany, we had a heavy rain in the western part of Germany, and our neighboring countries, Netherlands and Belgium, have also been affected. And this is a real challenge to all of us. And for those who do not believe that, please take a look at this website. I don't want to play this video right now because it takes too much time. It gives you an impression from on the basis of the recently published IPCC climate report and gives you an impression of what is happening on our planet and what should have been done very quickly. So, the next slide gives us an idea about the expectations of the future developments of the electricity supply. So what we are starting in this area, and what you see is that the share of electricity supply of offshore wind has the biggest growth of all. This is expected. And this graph here ends at 2050. We know that there are plans in Europe to reduce and to have a carbon neutral society by 2050. So this is a very important date in our considerations. The next slide shows the European development of wind energy. We see here the years. We are here now in 2021. This is an outlook for the next 5 years, and we see new installations and cumulative capacity. Today, we have reached 220 gigawatts of wind energy in Europe. What does it mean? 1 gigawatt, how much is that? A typical medium-sized carbon-based or coal-based power plant has a size of 1.3, 1.4 gigawatts. So just to give you an impression where we are. 220 we have today, and this is a rise up to 2025. So what we see from this picture is that we expect an increasing share of offshore wind energy. And to give you an impression about the current situation, this is Europe installed in the first half of 2021. We are here, and what you see from this slide is that we have a lot of installations in UK. This is UK, dark blue, and light blue, this is Germany, in the years 2017, 18, and 19. But a dramatic decrease in recent years. The reasons in Germany for that are clearly political, and this is annoying me very much. This has to be changed very, very quickly. So what we see is an annual increase in the area of 3 gigawatts. Is here, 3 gigawatts in a year. So what do we need? This is the current situation of offshore wind energy. So the majority of turbines have been installed in UK, some of them in Germany and Netherlands, Denmark and Belgium. We have now 26 gigawatts. And what is required in the world, based on the IPCC report, we have to install 230 gigawatts offshore, nominal power of offshore wind turbines by 2030, in Europe 60, and by 2050, 1,000 in the world and 300 in Europe. What does it mean? For the next 9 years, we have to install 60 minus 26. That means 34 gigawatts in 9 years. I think this is possible because what we have seen in the last slide is that we had a medium new installations of 3 gigawatt already. So an increase from 3 to 4 is possible with our companies in Europe. But what is a challenge is the period from 2030 to 2050. In this period, we are going to install in Europe 240 gigawatts. And that means we have to increase the installation, the annual installation, threefold. And that will only be possible with boosting industrialization in this area. So one of the options is, and what we see already today is, that we increase the size of the turbines. So these 241 turbines have been ordered in the first half of this year. And when we take a look at the turbine size, we see here Siemens Gamesa 7 megawatts, but also Siemens Gamesa, the biggest one, 14 megawatts per turbine. This is Vestas with about 10 megawatts per turbine. I remember well that we started in the year 2009 with our research wind park in Germany with turbines of 3 and 5 megawatt. So nowadays we have reached 15 megawatts per turbine, and this enables us with a reduced number of turbines to reach the goals we should reach. So what kind of wind energy support structures do we have in the offshore situation? Short look at this different structures tells us that we have monopiles. This is a simple tubular construction. This is a tube up to 8, 9, 10 meters diameter, rammed into the seabed and then connected to the tower, and the connection is normally above the sea level. Then we have this space frame structure with tubes, what we call jacket, and we have some special applications with tree piles and tripods. So a very short evaluation shows us the following. The monopile is very heavy. We have weights of only the monopile, that is up to this area, of about 2,000 tons. 2,000 tons, please consider the Eiffel Tower has a total weight of 10,000 tons. So it's 2,000 tons per monopile. This is very simple in the production. So the majority of the costs for this monopiles is due to the steel, the material. Then we have the jacket construction. The jackets are favorable in terms of weight, but unfavorable in terms of production. There's too much welding, up to date manual welding. Tree piles and tripods turned out to be unfavorable in terms of weight and production. And for that reason, we had only one wind park with this tree pile construction, and we had our test wind park in Germany and 2 other wind parks with this tripod constructions. In the meantime, the companies producing these tripods have went bankrupt. And if you ask me, in my opinion, this was predictable. I have given a presentation on a European conference in 2005 predicting that monopiles will be in front. And that has become true. And the statistic tells us this truth from all the wind turbines installed in the world. The 80% of the wind turbines stand on monopiles. So this gives you an impression of the size of these monopiles. And if you look at this statistic, the majority is monopiles, as I mentioned, and then we have the jackets. So I will address both of these in my presentation. Just to give you an impression of the size of these monopiles, this is a segment of a monopile in Germany at EEW. This is me, by the way, 10 meters diameter. Then we have the jacket here, and we have the tripod here as well. And the next slide shows us the tree pile here. in the Bad wind park, and this is a rather new kind of support structure. I will come back to that in some minutes. That is a jacket structure with so-called suction buckets. And we don't have to forget that linked to the offshore wind parks, we have these heavyweight jacket structures for the converter stations as well. I'm not going into detail in my presentation with that. That brings us to the research topics. The research topics, before I start with the details, I give you an impression of our research infrastructure. In Hanover, we have a so-called research campus of our university in the west of Hanover, in Marienwerder. And on this area, we have in 2014 opened a test center for support structures. I will come back to that in a minute. On the right-hand side, you have been watching a video from our big wave flume, which is now going to be expanded. It has a total length of more than 300 meters, one of the biggest facilities in the world. And in this area, we have big 3D basins for investigations as well. So that let us have a look into the research center. So in front of here, we have a big sand pit with 10 meters depth, where we investigate soil structure interaction, for example. This can be filled with water and sand in combination, so that we have offshore conditions. In the back, you see a strong wall and a strong floor, where we can investigate structures like this. This is a typical tubular connection. And we have other facilities like this resonance testing machine with an capacity of 1 meganewton and 100 hertz. We have in addition a climate chamber and autoclave for fiber reinforced plastics. Now I start with research projects. First of all, grouted connection. What is a grouted connection? It is a tube-in-tube connection where the load is transferred by this area with a grout. Grout is, so to say, a high-strength concrete. The strength is about 100 megapascal. So, and what we see here is the transition piece. We have this transition piece connected to the monopile with this grouted connection. And we started our investigations with fatigue tests on these grouted connections. We see here the grouted connections. To improve that, to decrease the overlap lengths. And we see here in the middle again how this works. The grouted connection, we have transition piece and the monopile connected via this grout connection. And what you have seen here in the middle of this grout connection is one of the outcomes of this first project, that we need these shear keys. At the beginning of the offshore wind story, there have been hundreds of turbines without these shear keys. And in 2008, we published a paper on a European conference saying that the existing design rules from DNV were misleading, and that we are not expecting that these designs will give the expected load-bearing capacity. 1 year later, the first damages occur in the North Sea, in UK and in the Netherlands, and more than 600 turbines were affected and have to be repaired. So this was one of the results of the first project that shear keys are obligatory, and then we started investigations on actual loaded grouted connections, which is typically the situation when you have jacket constructions. First of all, we tested them in dry conditions and developed a design method for that. And one of the things we learned from that project was that the model of a uniform longitudinal shear was obviously wrong. In this case, we have no uniform shear distribution in these shear keys, but the outer shear key connections are have much more load than the inner ones. So we have to investigate a non-uniform loading of the shear keys with appropriate finite element models. As most of these connections are not above water but in submerged conditions, we started investigate like this here in a typical jacket foundation. We started investigations with submerged grouted connections, small scale tests, big scale tests, and we found out that the water has a detrimental effect on the fatigue resistance. And the reason for that is that the grout particles in the vicinity of the shear keys are washed away from the water, and the shear key area then has gaps, and they provide a clearance in that area and leading to bigger deformations. These investigations lead to the PhD thesis of Alexander Raba, and he developed a design method for these submerged conditions as well. This is the story about grouted connections. Then we switch to bolted connections because the industry when I talk about bolted connections, in this case, I'm talking about this kind of ring flange connections where the bolts are subjected to axial forces, mainly. A little bit of bending as well. So we see here the typical ring flange on top of the monopile. The monopile is ramped into the seabed, and then we have a connection to the transition piece with a bolted connection. And the first bolted connection has been applied in 2014. This one in the connection between transition piece and the monopile. And in the meantime, all the grouted connections have completely substituted by bolted connections. And these bolted connections have been applied in earlier days in the tower, of course, between the different tower segments. But this bolted connection between transition piece and monopile is a very big one, as you can see here. This is only the bottom part of the connection. Yeah, this is this dimension, and you have the upper part in the same magnitude as well. So for these connections you need big bolts, and then the question occurred, what is the performance in terms of fatigue with these big bolts? You all know the influence on fatigue of the size, and for this purpose we have to use our 10 meganewton machine testing device here, and very big adapters for these big bolts to investigate the fatigue performance of these bolts. We have two influences. One influence is the large size, And the other one is the hot dip galvanizing, which has also a detrimental effect on the fatigue performance. Both have been investigated by Mr. Eichstätt, Rasmus Eichstätt, and in his PhD thesis, and he found out that the test results are in line with the existing fatigue classes for actual loaded hot dip galvanized bolts according to Eurocode 3. So everything is okay up to now. We don't know how much the bolt sizes will rise during the next years. In the meantime, many companies switched from these HV bolts to so-called stud bolts. That means we have threads on both sides, and on both sides we have these nuts and washers, and this leads to the tensioning method that we tension the bolts with tightening tools. Okay, so far are the bolt connections. Before I go to the welded connections, I want to give you the reason why I put this hydrogen picture here. And the reason is that the future of steel production will not be based on black coal like today. The reduction of the iron ore, not by black coal, but by hydrogen. And this hydrogen is taken from the electrolysis from water. And for this electrolysis, you need electric power, of course. And now you have this symbiosis between the steel industry and wind energy. So for the wind energy, we need, of course, steel. But for the steel in future, we will need the electricity produced by these wind parks by hydrolysis and providing us with hydrogen for this chemical process. So we have here the iron ore, which will be directly reduced with hydrogen to get these smaller parts and put these parts into an electric furnace to produce our steel. And this results with steel and water. This will be the future, and the steel industry is intending to reach this future and reduce the carbon dioxide emission from today to 5% of today until 2050. And very clearly, to reach this goal, we have to invest billions of euros, and it is estimated that the steel price will rise by 50%. What does it mean in terms of offshore wind substructures? I've been telling you that the jacket is favorable in terms of weight. With increasing steel price, the weight becomes more important. And when we, in parallel, reduce the production costs by automating the production process, then the jacket will become more competitive in comparison to the monopile. So this is the idea concerning the robot process into the welding process of these jacket support structures. We have prefabricated tubular joints. Then we connect with orbital welding the joints with prefabricated tubes. And Mr. Schaumann, one of my former assistants, who passed his PhD exam at the beginning of this year, has investigated these tubular joints here and demonstrated that the fatigue behavior of the automated welded tubular joints is better than the manual welded tubular joint. These tests have been applied using a special measurement system, which becomes more and more general in the steel research. That is a digital image correlation. And what we can see here from this movie is that this measurement system enables us to identify the beginning of the crack in the tests. So what you see here is the beginning of the crack on the cord size here in this situation during the test. This has been published in this thesis very recently during this year. And this brings me to the next research topic, suction bucket. Here I'm addressing an ongoing project which is led by the Fraunhofer Institute here. This is a picture of our test center where we have first investigations about this suction bucket. I will shortly give you an impression how this suction bucket works. In my next slide, you see here where we have these suction buckets at the bottom of the jacket structure. These suction buckets are quite big, and the idea is to generate a vacuum, and this is of course causing compression in this shell structure. So if we suck the air from this bucket here, we have here a vacuum, and this causes compression in the shell structure. And this is of course a critical situation for the shell. And those who are familiar with shell buckling problems know that we have a severe influence of the boundary conditions and of course of the imperfections. And Mrs. Bohm, the co-author of this presentation, gave a presentation on the recently Wind Energy Science Conference, which we have carried out in May this year with more than 750 papers on this conference. Mrs. Bohm gave this presentation where she investigated the different soil parameters impact, that is, so to say, the boundary conditions for this buckling problem, and she applied the probabilistic methods where she applied the statistical distribution of these soil parameters in her numerical investigations on the buckling of these structures. So this is about shell buckling. And last but not least, I want to address a corrosion project, one of the corrosion projects we are carrying out right now in our institute. We have harsh environmental conditions in the offshore situation, of course. And although we are protecting the structures with paintings, we cannot completely prevent corrosion. And to renew this protection on site is extremely expensive and difficult. And thus we are interested in the impact of this corrosion. So area corrosion is not the real interesting case, because we know the corrosion rates under free corrosion, and we can stick to that, and we can take that into account with a corrosion allowance. But what we cannot really quantify is the impact of these notches here from the pits, from pitting corrosion. And this is what we are addressing in the project. The project is again supported by our Federal Ministry of Economic Affairs, and the name of the project is EasyMo if you want to look at this in the internet. And our idea is that we take a scan of our specimen to identify in detail the surface conditions, then transfer the surface conditions into a finite element model, and with this finite element model investigate the stress concentration in our specimen. So you say this is fine for the test specimen in our laboratory. What are we going to do with the foundations on site? So this is very clear, and we developed an idea which you can say we took from our dentists. We produce replica with a specific kind of material. It's not the same what our dentists are using when they take replica from our teeth, but it is an excellent material with which you can use for a short period, which is flexible for a short period and then becomes hard and remains in the volume. This is a special kind of material, and it's going to be patented, not by us, but from one of the companies who are involved in this joint project. So, and then we investigate the surface of this replica with the same results that has been checked already. So, and then what we are going to do is, and what we have done already in a number of tests, is we investigate this corroded specimen in our test machine and to determine the fatigue resistance. And what you see here is again the application of this digital image correlation system, and exactly where we found out that the biggest notches have been in our specimen, exactly in this place the test specimen started to break. So it gives an excellent, not for all the specimen to be honest, but it gives an excellent impression that we can take from these surface investigations an idea where the main notches are and where the cracks are going to start. This brings me to the end of my presentation concerning the research, and I would like to sum up. So what you have seen, offshore wind energy is indispensable for future development. Cost reduction is a permanent issue. Industrialization is the key, and what I did not address in my presentation is that in future we will have challenges with floating structures. This is a completely different area in comparison to the bottom fixed structures which are mentioned here. And in addition, expanded lifetime of the wind parks will increase the requirements concerning fatigue and corrosion. I would like to mention that the contents of my presentation has been published already in an expanded version in the open access journal Steel Construction, so please take a look. At the end of my presentation, ladies and gentlemen, I would like to give you an appeal for the future. Most of you are younger than I, very much younger, and I will retire next year. Maybe this is the last talk on a Eurosteel conference of me. I spend a lot of my professional time contributing to renewable energies, not only wind energy, but others as well. The future is yours. It's your responsibility and task to save our planet, to be a safe home for humankind. Thank you all, and all the best to you. Bye bye.